Hello fellow engineers and welcome to the game that I did not expect anyone to enjoy watching, but actually the first episode did really well. It was in fact one of the best videos of the entire year last year.
Are you sure about that?
Yeah, but this time the devs gave me access to the entire game, so there's no restrictions, which means I can properly nerd out. Anyway, to start with, we will do the level we did before, but we'll build the entire network for the entire town. And then assuming this video does okay, maybe we'll go on to the next level and the other level, which adds some other stuff.
No! God, please, no!
So, let's get into this. So, if you never saw the first video, basically, I can't believe this game exists, honestly, it's so niche. But basically, this is my day job, but in sort of a video game form. It's more like a student learning tool, but we need to use real life engineering. And I'm not saying like video game engineering. This is legitimately real engineering. Like this is my day job, but they've added graphics to it. Whereas I was like looking at a spreadsheet and I was sort of seeing like this in my head. All right, so when you're looking at to do drainage, the first thing you want to do is sort of look at all the falls, look at your surfacing. So you got tarmac here, which obviously the water's going to land on and we need to drain that. You've got grass over this way, which most of the rain will soak into the grass. Some of it will roll onto the highway though. You've also got loads of driveways as well. Now remember, all of these, they're all concrete. So generally any water that lands on the driveway will make it to our road. Hence why, at least in the UK, you do need planning permission if you're going to turn your front lawn into a driveway. Because they need to check, like, if all that extra water's coming onto the road, can the road drainage handle it? Anyway, you'd send your surveyors out to go do this. They'd probably use, like, the standard surveying equipment, like a total station. And they'd just go around, like, doing spot levels everywhere. Then they'd shove it all together, make a nice triangulated surface. And that allows us to kick out contours. Now, contours look like that, and they basically just show you the levels of everything. And contours are like just really nice for like visualizing like highs and lows and stuff. If you don't know how contours work, basically each line is like a level. So if I hover my mouse over that line, you can see down the bottom the Z value there. 256.4 meters. That's like the level above sea level generally. So if we go to the next one, this is going to be 100 mil lower. So 256.3 meters. If you were to go from this line perpendicular like that, you're going straight downhill. So you hit that one and you're at that level, you're going straight downhill. And it means when you've got a road like this, like with a point, it's really nice and easy to see that the road is falling from the middle point over to like the curb line of each road. So it's falling from here over to there. We call that the camber of the road. And it's also falling from here down to the right. Hence, when you do the perpendicular, you do that sort of angle because that's the two falls like combined to go downhill. But if we just hover our mouse there, you can see 256.4. If we go like there to the middle, you'll see that is higher. 256.58, and then as we go back that way, it goes back down to the 0.4 value. So basically there's a high point along the middle of the road, but we can see it makes like a nice arrow. You can see the entire road's falling down this way where it gets to a low point down there. And also there's a junction here and there's another low point there. So up that way, that's up to a high point. Over this side, there's, oh, get out the way tree. There's another high point there. And I reckon this is probably a nice little stretch to do the gully spacing on. Now, generally when we do drainage, at least in the UK, at least my experience, we tend to do gully spacing and then the fluid simulations completely separately. Mostly because it's like way too much detail to put like all your little gullies and all that stuff into a simulation. It'll take way too long to run. But in this game, you actually do. So to start with, we want to go to create storm network, and then we can select what sort of inlet we want. Now, as I said before, as a Brit, I'm all about gully pots. So you can see it's just like a big square box, like a concrete box with a gully grating on top, a metal grating. So water enters that, ends up in the gully pot, and then we connect that to our pipe network. So what you'd do, you'd go up to the high point, and then depending on whether you're working like for the council on like a local road, which to be fair, that's probably what this would be. Like it's a housing estate. It's not going to be like a big trunk road or anything. So you would use the local standards. And that would be literally just work out an area that contributes to each gully. I don't know, call it 100 meters squared. So you'd go from your high point, you'd draw like your area out. And then you'd put your gully wherever that 100 meters squared is. And that area, it does vary depending on different councils. They all have their own sort of standards, their own way of doing it. So depending on where you are located in the country, you might do it differently. But I think this game, it's a bit more serious. It does it like how you do it for trunk roads, like the fast roads in the UK, the ones that need to be done properly. And that is based on the flow width. So if you think about when rain lands on this road, remember I said it falls like not only down that way, but also to the side. We can run a storm event. So if we run that basically simulates the rain falling, and it should show us exactly where the water goes. Oh, it does. It just does the final bit. Okay, well, yeah, the water ends up down there, but it would have run down like the side of this. So what you want to do for at least UK standards, generally you want to make sure you got a 1.2 meter width. So if we place one gully down and then we run that storm again, you should see, yes. So from the high point, which is here, you can see the water is running along this edge. It's then running down this way until it enters our gully. And you can see as it enters the gully, the water all goes into the gully, which means down this side, the flow width is like nice and narrow again. You can see it gets wider and wider. So generally the widest point is like just upstream of the gully. So we have this tool here, measure distance to gully, and you'd space these in the UK so that they're at 1.2 meter flow widths. Of course, it does depend on the width of the road, the width of the edge and stuff. But basically, it's the point at which a car's wheel would start to touch water. Oh yeah, I can move this. Okay, so we want to move this downstream until it gets to a point where there's 1.2 meter spacing. When we actually do this, we have like a big Excel spreadsheet. And in that spreadsheet, you'd basically put in all the different variables that might affect it. So it's going to be the area contributing, of course. And remember, that changes as you move it. So generally, you just put in the contributing width of the road, the width of the verge, any other things. So if there's like a driveway and stuff, you'd include that in there. You'd also put in the fall, so the long fall, the cross fall. You'd put all those values in, and then also the type of gully it is, because depending on what the grating's like, etc., depends on how much water can enter this. But yeah, so basically, you just go along changing values until you get, oh man, we can put this really far down. Flow width there is only like 70 centimeters. And I think that's because there's not actually that much contributing to it. I think if we click on this, we do actually get, yeah, look, it tells us all the different materials. It tells us the area of each one. It also gives us this coefficient. Now this uses the rational method. I won't go into it too much. It's kind of boring. But that uses a rainfall intensity, which varies depending on what part of the world you're in. The wetter parts, that number will be higher. It's measured in millimeters per hour, so it's like the rainfall intensity. Well, that was quite obvious by the name of it. It's then got the area, so all of these values. Now remember, as we move this away from the high point, that increases. If we go close to the high point, that decreases. And then we've got the runoff coefficient, which is basically each of these materials, as I said before, like for asphalt, we're assuming 90% of the water that lands on it will make it to our gully. The 10% will just soak into the asphalt. For the lawn, only 20% will like run off the lawn. 80% will soak into the ground, so we don't have to worry about that. Because remember, we're only worried about the water that makes it to this gully. So I imagine I have to move this down probably quite a long way. What I'm going to expect is that 1.2 spacing will probably be like over here somewhere. But if you look, can you see our curb disappears? Because we've got this driveway here. We've got these which are called drop curbs. And then this is flush, so there's no upstand. Upstand being like this vertical face of the curb. And that means the water has nowhere to go. So as an example, if we were to move this gully, let's just say to like there-ish, we'll run the storm again. What you'd see is your flow width getting wider and wider, but then when it gets to here, because there's no curb, you're just flooding like the driveway here. So generally, if there is like a drop curb like that, they're often used for like pedestrian crossings is where you see them most often. But you would always put a gully like upstream of them like that, so that when we run the storm a final time, we're doing everything we can to minimize the puddles there. It's 107 centimeters flow width, so I think that's good for our first gully. And we've got to do the other side of the road as well. And to be honest, because they're symmetrical, it's probably going to be the same, although the grass width may be wider. I mean, we'll try go completely symmetrical. And then, yes, look, can you see how much wider that flow width is? 1.8 meters. That's why you really need to be careful of what's contributing aside from just the road. This side has a much wider verge that's contributing, I guess, because the fall's here. So if we measure back that flow width till we get to the 1.2 location, so that's about there-ish, that is where we want our gully to go. Because we know the flow width will be 1.2 and then it'll go small again. So assuming it's small again, I imagine our next gully will go around about there. So we'll run the storm and then hopefully we'll see just under 1.2. So that's good. And then it goes wider again. And oh, it does go a bit wider. Now this shape is a little bit funky. You would expect like sort of a straight line there. I think it's just because like how the catchment areas works. Like it's measuring all the way from back here. Now that's, you gotta take some common sense into this. Whenever I measured like the contributing verges, I would probably include like this bank as the width. I wouldn't go all the way back there. Like it's nonsense. Maybe if it was really steep, but like it's flat. I mean, look how flat it is. Yeah, so if we go look at this, the lawn area contributing 862 meters squared. Which is a bit crazy. I mean, if you imagine the entire country sloped, like imagine it all sloped like all the way from that mountain. Technically, if you don't apply common sense, you've got to include all of that because water landing on that mountain, it could flow all the way along here, all the way down to this road. But like it's miles and miles of flat terrain in between. It's not really going to make it over this way. Right, so anyway, we're working our way down. I will just move these gullies about just so it does do the 1.2. We can do some quick wins by putting gullies upstream of the driveways and stuff. But then we get to this point, the low point. Now, what you would do, you'd always do your spacing so you've got your 1.2. So if we measure this, you can see we got 1.2 there. So we'll shove a gully about there. And then the next one, you'd probably find it goes like past the low point. So what you'd do, you'd just put it at the low point. So your low point gully should always take less water than like your upstream ones. That's because it's at the low point. It's pretty important that you drain this spot because this is where it's going to flood if it's going to flood. And generally as well, we'd put a double gully in because you'd have this one which is taking the water from this side. You'd also do the same when you're working like down the other way. So you'd end up with two gullies sort of on the same location. So if I put that one like there, hopefully I can put another one next to it for the other side. I think for now, let's just run that and see if it does simulate this side properly. It might not because it's a low point. It's got the other side. Oh no, it has. So you can see we've got the 1.2 flow width there. Down here, similar thing. We get to about 1.2 where that goes in. So if we go to the high point on this side, and remember the high point on this side is of the curb line. So the high point is actually there. Like if you look straight down, you follow these contours. Water landing on this side will go that way and then flow that direction. Water landing on this side will go there and go that direction. So for this one, our high point is literally that. So if we measure to try and find our 1.2, you can see it's there. There is a driveway there. So I'd probably shove that upstream. And then our next one is just going to go at the low point. So it looks like as close as I can get to that one is there. You would put them literally like right next to each other. Oh, anyway, I've just run the storm with the double gully and it doesn't actually show any flooding, so that's good. So I've just gone along. I've done like all of this road as well. Generally, you'd expect to see like quite consistent spacing, but I think because how this works, because all the grass that's included and because there's like gaps in the houses and stuff, like that's upstream. We got a driveway there, so I've put a gully downstream, but I had to put one like literally right downstream of that as well, just because I guess the width was so long. Like I think this orange line here shows like the contributing area and it's just massive. So that would be like a sort of complaint I had about this game. It takes the grass area a bit too literally. You got to apply a bit of common sense. Anyway, I've done the gullies up over this way. You can see the only sort of issue is where we've got this driveway just because there's no curb upstand. You can't have a gully in there. Even if you try and put one in, game just says no. I mean, in reality, you probably could put one there. I mean, hydraulically it would work. I'm just not sure about who owns what. As I say, I'm more of a big road man than like these little housing estates. So it's all a bit different. Like what I was saying earlier about putting putting gullies upstream of these droppers. You'd only really do that for like pedestrian crossings, so people don't have to walk through a puddle. I don't think you'd actually do it for someone's driveway, but we always need one downstream because that's taking all the water of the driveway. And I guess typically we do just put one upstream because we want to reduce that amount of water. So again, down here, if I just do there and there, and then we've got our low point over this way. So we'll do the double gully thing that I've been doing. I don't think you're meant to be doing double gullies in this. I think I should be using like a different inlet, but I don't like how they only have like one grating. I mean, that doesn't have any grating. Maybe they're better to use. Don't know. I think I'm better off just doing it the British way, the double gully, even though they should be like touching, as I said before, pretty much. Oh, actually, maybe we don't need one upstream there because look, that's only 80 centimeters flow width. And down here upstream, it's only 80 again. So potentially, if we remove that one and then run it again, is the flow width here going to be suitable? Yeah, look, it doesn't go over 1.2 meters. So that's 93 centimeters. I mean, we'll give it a go down here. This could be a bit closer, but run that storm. And oh, yeah, look, it's 1.27. Oh, that's so close. But standards are standards. If it's over 1.2, you got to put an extra gully upstream. All right, so flow width around here is fine until about that point. So we just shove an extra gully there. Is that showing where there's loads of water coming from like the adjacent land or something? Potentially. Let's shove a gully there. We'll then run again and we'll see how wide the flow width is there and whether that like weird symbol goes. Oh, it does go. But yeah, flow width is huge here. It goes up to 1.8. And yeah, man, there's so much water. I think it's just water coming from like all that land. Still, I'll just go around. I'll make sure all the flow widths are below 1.2 meters, and then we'll carry on. Right, okay, so our gully network is now in. And so once this is done, in real life, we'd go from our like spreadsheet. We'd then draw these on a drawing, and then we'd work out all the areas. And then we take that information and we put it into like our pipe modeling network. Now this, where we create the pipes using these manholes, we don't usually have all the gullies and stuff in there. We literally just model the pipes and then show the areas going to each pipe. Like we don't actually model the pipe going from each gully to these. Yeah, and it's something sort of kind of hard to explain to people, like apprentices and stuff, like when you're trying to teach them how to do drainage. So I actually really like that you do see all that stuff. Anyway, so these manholes, they're just a precast concrete ring, which is like the green bit under the ground, with a steel lid that you've probably seen.
Oh, really?
And these are usually used where pipes connect into like certain locations. For example, if you've got a load of gullies that you've got to get into a pipe, you make them connect to a manhole. But you also put them whenever your pipe has a change of direction or gradient, because generally that's where silt might build up. So these allow you to like access the pipe to clean it and stuff. And well, and just to inspect the pipe to see if it's flowing or if it's full of water. So in this situation, I think I'd probably start by putting these chambers on one side of the road or the other, or in the verge. Now in the verge is always quite nice because it means if you need to like repair the pipe, or if you just need to go into that manhole chamber, you don't need to put any traffic management down. You don't need to put cones out. You don't need traffic lights or whatever. However, because this is a residential area, I feel like all the verges here are people's front lawns. So we probably don't actually want to go on them because then we have to buy the land off them or buy licenses off them. So generally, we will just go in the road. Now, when you place chambers in a road, you want to, as I said before, bear in mind about traffic. So if you put these chambers in the middle of the road, you'd have to shut the road completely if you want to get into these, because cars won't be able to get past. If you had a chamber just on one side, then it means you only need to close one road direction and people can still like get around. But yeah, generally you start upstream. So I'm looking at contours. We got a high point here. So we want to start sort of up this way. Now the trouble is these gullies, they're all lower than up here. So in order to connect from these up to this high point, these pipes are going to be going against the gradient, which means they're going to get deeper and deeper. Let's shove one there to take those 3 gullies. We'll shove one there to take those 3. And then we can sort of head sort of on the diagonal. And I think we're going to go on this side of the road. So I'm thinking, oh, it keeps snapping to that. I don't want to go to that. Thinking if we go like there, And another one there. We'll go down. We'll do another one. You may be able to get away with down there. We need one there for those two. And then here is where we have our junction. Remember, we got our 2 low points. So what I'm probably going to do is do either 2 separate networks or just link them up like later, like over that way. So let's take those 2, those 3. And then at the low point, we've got a whole load of gullies. So we'll shove that right at the low point. And then it's from here, ideally, that we want to go. We want to try and get to our pond. Now, I'm saying pond because we have a pond in this example. Typically, though, you would just connect either to like a river or some sort of water course or into an existing highway network. Because generally, when the original highway networks were made, they had lots of capacity. And not only that, when we design these, when we limit the flow and stuff, we want to make sure we're not actually adding any more flow into a network than was there previously. So bear in mind, before all these houses, before this road was built, this was just a field. Imagine all the water that was landing on there onto the grass. Remember this rational method with the grass and the 20%? So basically all the area of road here, rather than 20% of it getting to that water course, there's now 90% of it going there because it's asphalt. So basically what we'd work out is before this was built, what the flow is going to there. When we design our network and stuff, we then get a new flow which is going to be much higher. What we do is we then limit the flow. And you can do that by actually using a pond. So basically all the water will come down into here, probably like a big old pipe because it's taking a lot of water. And then out of your pond, you'd have a smaller pipe, which limits how much water can get out. So it throttles it. Because remember, flow rates through a pipe, it's a volume per second. So if you limit that, you're reducing how much volume per second can get through, which means that extra volume has to go somewhere. And that decides how big your pond is. Because as less water is coming out of your pond, it starts filling up into here, but then it just drains like later on once the rain stopped. All of that is probably a whole new video, to be honest, so I won't go into that into too much detail. For now, let's just get this network done. So I want to go from the other end, which is like there, do a few manholes, and then connect to my one at the low point. And then from the low point, we're going to come out this way. Now, we've got to be careful. There's a telegraph pole there, so we don't want to go too close to that. Like, we definitely don't want to put our pipe underneath it. We've also got to bear in mind these are private properties.
Get off my lawn.
So we don't want to go like under houses. We don't really want to go like through their gardens if we can help it. We've also got to bear in mind the fall of the land as well. So you can see the road is like down at that level. This land is actually higher than this. So as we're going through there, our pipe's going to have to be, well, we're going to have to dig a really big trench. Yeah, so I reckon let's shove a manhole like there just to get out of the way of that telegraph pole. And then we'll do another one down this way, trying to stay away from trees as well. And then we'll swap to a head wall because this allows us to outfit into a pond. Yeah, and I think we'll just shove that like in the corner. And oh, look how small it was. It's so big in the preview. Yeah, so a head wall is just like a concrete, well, one of those basically with a pipe outlet in it. So it allows your underground pipe network to discharge at surface level, like into the pond. And you can see we've got some like stones and stuff down there just to stop this area of the pond getting like eroded and stuff. And you often add like big boulders and stuff to here just to like slow down the flow as well. Because if your water's creaming it into the pond, then it's gonna do some damage. Right, anyway, so that's a lot of our network done. We'll just do over this side, this little stretch. So I think we'll stay on this side of the road this time. Then we end up at the low point and then we go into the verge. Then I'm going to come around this way to about there. And then I'm going to go connect down to that one. Yeah, so that's our full pipe network. Oh, by the way, check out the label of that one. Manhole MH69. Nice. But yeah, that's our pipe network done. It's essentially in 2D though. And you might be wondering, well, why did you place them where you did? Like, it seems a little bit random. Like, yes, we know about the road and stuff, but what about the distances and stuff? So you never want to go longer between two chambers than 80 meters. So you can see, I think this is my longest one. It's 60 or just under 60 meters long. That's just for maintenance. So when people like come to a chamber, generally their equipment can reach like 100 meters. So generally you don't want to go too far, so people can still maintain it easily. But the other thing was so we can connect all of our gullies up. Now, when you connect gullies, you got to think about a couple of things. One is the level. So as I said before, we know that the gully here is lower than the manhole. Not ideal. But the other thing you've got to bear in mind is like the angles. So in order to connect into this chamber, which The ultimate aim is to get the water into this pipe down here. You've got to bear in mind, if you've got pipes coming into this, you can only have like so many pipes coming in. Otherwise they'll like start clashing. So a general rule is you can have one sort of straight in at the back, one at like 45 degrees, and then one at 90 degrees. So what I've done, I've just moved that manhole slightly. So this is more at like a 45-degree angle. I mean, we could move that back a bit just to make room. The only trouble is you've got to bear in mind these 4 pipes are all going into this chamber and this one's coming out. So you don't really want to have from this pipe, this angle here, you don't really want it to be less than 90 degrees because otherwise the flow of this is sort of like it's going back on itself. If you think it's coming into this chamber and then it's got to try and change direction and get out that way. Now that's just going to cause like turbulence in the water and really upset your physics and stuff. You want to keep that angle as 90 degrees. I think you can probably get away with that because these pipes are only, well, in real life, not in this game, they're only 150 mil diameter. So they're quite thin. They're quite easy to bend. So if you've got your 45 degree there, you can bend that. You can do that on site fairly easily. So basically, I'm just going to go around and connect all of these from every gully to every manhole. I've connected all of these up. You'll notice the inlets on this side because we got our outlet there, which to be honest is not at a very nice angle. Like we got our main pipe coming down there and then it's got more than 90 degrees there. Maybe worth moving this sort of a bit closer to those chambers if it stops snapping to stuff. So a bit more like that. As long as it's not in the center of the road, I think that's a bit better. And yeah, I'm going to shove these gullies over that way, except no, look, we have a telegraph pole in the way. If we were to go down there, the angles would be too small as well. But also that's in the way. All right, that's all those gullies down there connected. I will just do this arm as well. So same thing as before, trying to keep that 90-degree angle. So like here, I think these 3 gullies, we would just connect up to that one. But right, oh goodness, zoomed out, that is a mess. But that is our pipe network done now. We've got all the gullies connected to the pipes. So we know exactly how much water is coming through all this, which means we can size the pipes and we can put levels in and stuff. Because at the moment I haven't done any of that, and you can see this is simulating pretty accurately that there's too much water, and if there's too much water trying to get down your pipes, it's got to go somewhere, and that is upwards, and of course that will cause a massive flood. So what we've got to do now is we've got to add levels to either end of these pipes. You can see they are sort of, we can go under the ground so we can see what's going on. Yeah, so basically everything is flowing downhill, which is good. You can see the slope there. They're pretty much always minus 0.1%. I never did slopes in percentage. I always did like 1 over 10 or whatever, 1 over 100. I think 0.1%. That is 1 over 100, right?
Wrong.
But anyway, when you're working in pipe gradients, the shallowest you ever want a pipe to go generally is 1 in its diameter. And that's in millimeters. So because this pipe is a 300 mil pipe, the slope should be 1 in 300. Like that's as flat as you want to go really. And that's based on the flow velocity of water like through this pipe. You can of course work it out properly, and we probably should. I mean, does this give you a pipe velocity? No, it doesn't. Very interesting. But the pipe velocity, generally you want it to be 0.75 meters a second. Like that's how fast the water's flowing through it. I think 0.75 is generally the minimum. I think best practice is going for like 1 meter a second. But the reason you don't go lower than that is because basically silt builds up in pipes if it's lower than that. Whereas keeping it at that sort of speed, it keeps the silt always moving through the network. It's called the self-cleansing velocity because obviously it means it's self-cleansing. So I guess starting with our gullies, I can't choose the 150, so these are going to have to be at 1 in 300. So can I just say, make that 0.3? And has that changed the downstream invert level? Yeah, I think it has. So now this end of the pipe, it's at this elevation. And because that's the longest one coming in, that sort of sets the level for all the others. So basically, I think that is the value we need. 255.16. So that should be downstream of all of these. 255.6. Yeah, that one's good. That one's good. That one's not good. It's slightly too high. So, oh, actually, no, look. This one, because the upstream is lower, that one's not steep enough. So it's actually 0.14. So let's just change all the other ones again. So that defines the sort of minimum level this manhole is at. However, because it is in the road, we need to make sure there's at least 1.2 meter of cover over this pipe. Otherwise, this pipe will get crushed by the weight of the cars, unless it's encased in concrete, but that's very expensive, so we do avoid that. Now, looking at this manhole, you can see the depth is 1.471. So that's the depth from the surface level to the invert of this, like to the bottom where the pipe comes out. So what you need to do, you need to make sure that is at least 1.2 once you take away the pipe diameter, because that 1.2 meters is what sits above the pipe. It's not including the diameter, so you got to remove that, remember. But right, once that's all in place, we then go from this pipe, the next one downstream. We do the same thing, so 1 in, 1 diameter. That gives you a new elevation down here. So that changes this one so it's slightly deeper. And then you sort of just work downstream doing the same thing. But the thing to keep in mind is the level that pipes come into the manhole and go out. They generally should be the same. So it should be completely flat. You can have something called a backdrop where a pipe comes in higher. The water then drops down and the pipe comes out lower. But generally, you just want to keep them all at the same level. So you got to make sure when you work out your pipe coming in level, you then change the one going out. You make sure that's at the same level. So we can then start working down our network doing this. However, you will notice we've still got the same pipe diameter of 300 mil. And there's going to be a point where a 300 mil pipe is not sufficient. So it's probably worth instead literally swapping all of these to like the biggest pipe size. So at the very bottom, we've got our very biggest pipes, because remember, that's taking all the water of everything upstream. The ones up at the very top of the network, they can just be quite small because they're only taking a small amount of water. But as you go downhill, they're going to be taking more and more water. So we've got to make sure they are bigger pipes. So I'm just going to work back upstream roughly, making these all a bit bigger. Oh, so this works in real time, so you don't even have to like keep running your storm. Yeah, so what I can do, I can literally just make these a smaller pipe, because you want to use the smallest pipe you can because they're cheaper. So we've got to this point where now a manhole is popping. So if we just up the pipe diameter of that's now no longer doing that. So it means from this point we can just be the 380 mil, which is a random size. I think that'd be a 375 in the UK. Is that because I'm using concrete rather than plastic? Maybe. So yeah, we've got 375s down here. When I change this one to 375, this does pop. That is because, remember, we've got this road on the right all contributing as well. It's not just everything on the left. This is the point where two networks meet. So that probably has to be a 450. And yeah, that works. Everything to the right, this side, it's only a little network. It can be 300, so that's good. So then from this point, we're on the 450 diameters until we get to this point, which is when the manholes over this side also contribute. Let's see what size we can get away with these. So yeah, it looks like we can do 300s all the way down to the bottom, so that's good. And then where these two meet, we've got a 450 and a 300 coming in. So I'll try 450, but that may pop it. Oh, it didn't. Decent. So there's quite a lot of capacity in that 450, which means all of that works. But I do need to go back and now do all the levels, because I just roughly did this just to give us some idea of what we're working with. All right, so we've got there. We can have a look at check design. You can see my design has been rejected. If we scroll down to the bottom, that is based on we have storm pipes colliding. Now I've spent ages looking. I can't find where it is. It's probably like my angles there. Can you see those two pipes are really close together? Actually, what if I just move it to there? Does that fix it? Oh no, my penalty's gone up. Nah, still a failure because they're colliding. Well, somewhere two little pipes are colliding. But as I said, on site, you just bodge it. You just bend it around a pipe. Now, that's one thing I wish this game did do. It would actually show you like where your failures are. Like I don't know where that is. I have no way of knowing. But yeah, that is our pipe network done. It's a shame mine has been rejected because of that, but whatever. We spent 500 grand, which gives you some idea of like the cost of like putting drainage in and stuff. Particularly when you've probably never even noticed it in your life, aside from like manhole covers and gully gratings. You wouldn't even know beneath your feet, beneath the roads, there's loads of pipes and stuff. But now you do. So anyway, guys, thanks for joining. Hope that wasn't too boring. If you want another one, we can look at the next levels next time if you want. If you don't, I totally understand as well. Anyway, peace, love, and drainage. Bye.